Hi everybody, and welcome to our webinar on multimode waveguide interconnect systems. This is the 9th in a series of webinars presented by KOBO, which is the Consortium for Onboard Optics, and sponsored by DuPont's Silicon Valley Technology Center. So when we consider the future switchboard designs, the interconnect between components will need to scale both in the density of bandwidth while reducing the power consumption. In this webinar, we'll be discussing the use of embedded optical waveguides in the PCB and the requisite connectors and media adapters as a next-gen alternative to copper traces. So as many of you may know, last September, KOBO initiated a new working group to address multimode waveguide interconnect systems, or MWIS. Our first presenter today is Joshua Kim, who is the chair of that working group, and he's also a senior integrity engineer in photonics and electronics at Hirose Electric USA. After his presentation, we'll hear from Marika Immonen, who is a manager for R&D optical interconnects at TTM Technologies, which is one of the leading suppliers of advanced PCBs. So after this presentation, or after this webinar, which should last for 1 hour, we should have plenty of time for Q&A. The audience is welcome to submit your questions. Please use the Q&A function that you see at the bottom of the Zoom screen. And if you could please indicate if the question is for Joshua or for Marika, that would be great. We'll get to as many of the questions as we can. And so with that, let's kick it off. Let's get started. Joshua, the floor is all yours.
So good morning, good afternoon, good evening, everyone. My name is Joshua Kihong Kim, a principal engineer at Hirose Electric US, and the chairman of a new working group called Multimode Waveguide Interconnect System, in short, MWIS. MWIS has been formed recently at KOBO, Consortium Onboard Optics. The goal for MWIS is to scale performance in bandwidth and power consumption, especially beyond 100 gig per lane interconnect system in PCB. So let's take a closer look at the component of MWIS. MWIS is the optical interconnect system embedded right at the printed circuit board, along with conventional copper traces. The picture on the right shows the embedded optical multimode waveguide as an example. Here you can see a zoom-in small waveguide array, along with conventional copper traces and through-hole vias. These waveguides carry optical signal that is generated by EO converter and terminated by the OE converter, populated on the same PCB to interconnect between two chips or chip to module. As such, MWIS is composed of several elements to build a channel. There are a very thin EO-OE converter, which we call media adapter, or simply MA, and a very short copper trace to drive such MAs from existing SerDeSes. And finally, a polymer-based multimode waveguide itself with associated optical couplers. The details of this MWIS manufacturing background-related topics and some of the project outline will be covered by our next speaker, Marika Immonen from TTM. Before we share the details on how the upscale performance could be achieved, I'd like to share the implementation scope of MWIS in this slide. First, the optical waveguide is always terminated by a pair of media adapters. Second, MWIS allows some copper trace length, but doesn't exclude zero length copper option. Third, the least possible amount of hardware is recommended for MA implementation in order to reduce the overall power consumption, but just to meet the targeted channel BR. Because both optical and electrical channel length to be driven by media adapter is extremely small compared to the ones for the typical optical module that we are familiar with today, at least 50 times to few thousand times smaller. Finally, the channel performance in terms of bandwidth and power consumption should be assessed in the electrical domain with the optical channel inclusive. The figure at the left here shows two implementation methods, MPO-like implementation and CPO-like implementation, especially for chip-to-module application. What I mean by MPO-like and CPO-like is that one can restructure the existing MPO module, which has fiber as default interface, into the one with optical waveguide embedded in PCB. Same story goes to CPO-like MA implementation. A special note should be made here, especially for chip-to-module application. In MWIS implementation, unlike MPO or CPO approach, the conventional optical pluggable module can still be populated at the faceplate. This guarantees the backward compatibility in system integration perspective, while just in-box interconnect engines are upgraded for the future-proof hyperscale cloud. This shows chip-to-chip example to complete the implementation scenario. Now we want to move into the power efficiency topic. Let's quickly review the conventional copper channel shown in this box. The SerDes drive transmission line of characteristic impedance of G0 with the spec of insertion loss, return loss, crosstalk, etc., and possibly the stress signal spec at the RX SerDes through such lossy and impaired transmission line. Here I specifically mentioned about characteristic impedance because it is an important system parameter for the power calculation. As the speed of the copper channel increases, we know that the insertion loss of the Nyquist frequency is increased due to the PCB material and copper loss. This increases power consumption. But that's not the only one, as engineers have squeezed the bits into a Shannon limit. It also increased the number of bits dwelling in each physical discontinuities, such as connectors and vias. And we know that the natural recommendation for digital equalizers is to increase the number of taps accordingly. In short, the power consumption is no longer a simple linear function of operational frequency, but it becomes an exponential function of frequency. This chart shows numbers in red in here to tell how much each type of SerDes consumes power in average when implemented, compliant to the pertained specifications in here. Note that the numbers were collected from verbal communication with OEM vendors, so no guarantee is given to use for other purposes, but it provides enough information to use as a parameter which you want to change later if desired. In any case, as a summary, PCB copper connection limits its insertion loss 28, 20, 16, and 10 dB, depending on the application classes of channel, which are LR, MR, VSR, and XSR in OF term. Note that this is 100 gig SerDes with PAM4 technology based. Now we know the length in dB. We have picojoule per bit information ready. We could calculate the slope of energy per bit for a fictitious SerDes design. Or reversely, we can calculate by this how much power one could save if we reduce the copper trace length. From the first order linear curve fitting, we finally got energy per bit slope for copper of 0.35 picojoule per bit derived from the collected data. With this, as an example, if we can reduce the copper trace of X dB, then the power saving would become X by 0.35 picojoule per bit. This is important result for the architectural decision on whether MWIS approach for a specific application is appropriate or not. Now, let's look at the power consumption for MWIS case in detail. Like conventional PCB channel, TX SerDes should drive all the discontinuities, but possibly with very short length of trace of the specified characteristic impedance again. Then it is followed by the transconductance stage, LD, waveguide, photodetector, photodiode, transimpedance, and finally SerDes through the short trace again. Now, by comparing this with the conventional copper channel shown in the upper box, we have SerDes is in common between the two. The only difference is power consumption is its additional MA blocks. With the possible scenario of optical losses and the worst case of pixel and PD operational conditions, and with simple transconductance amp and transimpedance amp with their gains to compensate the possible optical loss in multimode waveguide with related optics, we ended up with 352 femtojoule per bit maximum power consumption for this particular MWIS channel example. Note that the number is not coming from the exhaustive analysis, but rather to get the first order hint for the viability check of the method. Now we assuming an MWIS channel is equipped with the fictitious SerDes designed by the design law of energy per bit slope derived in the previous chart, and with minimal copper trace of 1 dB interface. Now we have, through simple math, 0.7 picojoule per bit or sub-picojoule per bit overall power consumption, even with MAs, media adapters. This result may be compared with 6 to 10 picojoule per bit of typical power consumption of LR application, which has comparable interconnection length to this particular MWIS channel model. Now let's switch gear to the channel bandwidth topic. The optical channel model is composed of optical connector from light source and multimode, including possible misalignment, demiss, between the coupler and waveguide, considering the assembly tolerances. For this simulation, we have used eigenmode expansion tool with the configuration setup of maximum mode number of 100. Here is some animation using the field plots by increasing the length of multimode waveguide. This shows the dual nature of optical signal in the waveguide, that is, wave and ray nature of light, which are coexisting in this simulation due to rather larger physical dimension we are dealing with compared to intra-chip dimension of silicon photonics application. So it is very important to perform optical signal integrity analysis based on the extracted S parameter for holistic EOE simulation. This chart shows impulse response of the optical channel model. The upper row shows 25 centimeter long multimode waveguide with a varying misalignment distance in micrometer, and lower ones shows 50 centimeter long case. As you can see, 50 centimeter multimode waveguide channel shows more pulse broadening than 25 centimeter one. More importantly, there is no extra modal impairment due to the possible mode disturbances from any optical misalignment, as opposed to what we had initially concerned about. However, we have seen non-monotonic decrease of power due to the wave nature of optical signal as you increase the displacement from 0 to maximum of 14 micrometer. This chart shows top-level block diagram of MATLAB simulation code for the signal integrity analysis of the holistic EOE channel and some results of waveform and spectrum at each test point before and after electrical TX filter, after multimode waveguide, optical domain, the electrical RX filter. In here, no digital equalizers are yet applied. Starting from left, baseband NRG pattern vector enters into this multimode waveguide through frequency up conversion to around 300 terahertz carrier frequency domain and experience optical S parameters as 2-1, and goes down conversion back to the baseband domain with linear electrical filter, in this case Gaussian filter. As you can see, the proper electrical filter setting, it shows wide open line at in this figure. This chart shares further details on the eye diagram analysis. Left column shows a 100 gig case with no filter, second with TX electrical filter, and the last one is TX and RX electrical filter, both on. So the last one shows the same eye diagram that I showed in a previous chart. Shifting to the next column, it shows how eye diagram degrades as we increase the speed from 150 to 250, even with both filters on. You could see more modal impairment appears as you increase the speed. The last column shows eyes at 250 gig speed with both filters on for misalignment, in this case, for 0 and 7 micrometer and 14 micrometer of misalignment. Considering 48 by 48 micrometer multimode waveguide structure, 14 micrometer is about 30% of the waveguide feature size. With this offset, it still shows the wide open eye, but with reduced average optical power, which can be linearly amplified by transimpedance amp or transconductance amp. However, most importantly, the modal impairment does not change its shape even with the varying misalignment amount which is very encouraging and important result, since MWI's implementation scope allows electrical SerDes to equalize such deterministic impairment as purposedly designed. This is the last chart for summary we have reviewed. PCB embedded polymer-based long optical multimode waveguide with very thin EO and OE converter called media adapter, together with very short copper trace, forms a newly proposed interconnect system called MWIS. MWIS architecture has been reviewed as a future-proof solution for a new PCB interconnect system in the power consumption and bandwidth breakthrough perspective. MWIS channel can be implemented with extremely lower energy consumption, even with the addition of EO-OE module. Optical S21 is extracted with misalignment variation and reviewed through the channel impulse response to assess the modal impairment. Eye diagram with linear electrical filter shows promising result. However, nonlinear time-varying filters can also be further applied as an encouraging next topic, where electrically equivalent S21 is to be formulated for standard and industry activity. With the dedicated electrical SerDes and filters for MWIS channel, there seems no fundamental limit to scale up the bandwidth to 200 and 300 terahertz of optical carrier. This concludes my presentation. Now, next presenters is from Marika. Now it's your turn, Marika.
Thank you, Joshua. Okay, good morning, good afternoon, good evening, everybody. Thank you, Joshua, for the introduction. So now we are going to continue with looking at advanced PCBs with optical waveguide interconnects on the ecosystem readiness and technical, let's say, attributes, how the boards are being built, what's the technology readiness level for these boards. And I'm going to directly jump into the Ethernet bandwidth speed transition roadmap. So obviously, industry roadmaps are driving us for higher speed. We are seeing the switch capacity doubling every 18 to 20 months, either in the number of channels or the channel speed. So currently, we're seeing that 100 gig SerDes is being implemented in systems, and the 200 gig SerDes is ahead of us in very near future. These speed transitions and high-speed channels are really driving material selection, testing requirements, via structures, and many other critical design attributes in our PCBs. So 100 gig node is already the speed node that we are seeing the transitions from copper to optical, especially for example, in the form of a CPO and other technologies. So moving on, describing or discussing the Electro Optical PCB that we're discussing. Here is a schematic of an PCB with waveguides. So the scope is really to provide additional high-capacity optical tracing layer, part of a regular PCB, which means that we can add on the optical functionality into regular products with copper layers and interconnects. This means that we are adding functionality where it makes sense, where it provides value. Obviously, besides the optical waveguiding layer, the tracing layer, we need optical connectors and coupling structures to couple light in and out from the waveguides to the devices, and in some applications off the board. This schematic indicates one potential construction, but obviously the optical layer can locate virtually in any layer in the stack. However, the optical coupling solution usually sets some mechanical requirements for the layer location in the stack. The technology that we are going to, let's say, look at in the following slides will indicate that the technology is scalable and it fits to various products and form factors. So we can implement this optical waveguide technology into modules, cards, and backplanes. Here is a fabricated or an example of an OE PCB product with 16 couple layers and 1 optical layer. So obviously this cross section shows us that the optical layer built here in the middle of the stack provides the channels part of the regular product. The changes are minimal, but still adding these highest speed or replacing the highest speed signal layers by the optical waveguides. We can see here 14 plus 14 channels built in a regular product with all microvia layers, plated through holes, and other electrical functionalities. Here, obviously, we have developed the process to support that. The materials are compliant, and the process can be handled with the regular PCB factories. So moving on to discuss on the fabrication itself, optical layer and the materials that are intended and developed for this application obviously needs to be compliant for the rest of the PCB, the couple layers, the dielectrics, the processes that we have. Here is let's say simplified schematic of the process, how to build the waveguide, the waveguiding layer. It fundamentally constructs of 3 layers, 3 optical material layers. We call it clad 1 optical core and clad 2. They form the similar structure as we see in a fiber. So we have to have a optical tracing, optical signal carrying core surrounded by all its sides with the cladding. So we can start the fabrication from a naked core or a subcore. We deposit the cladding, the first cladding layer onto it. The methods that can be used depends upon the material. If the material is a liquid, obviously we follow the liquid material coating techniques. If it's a dry film, we can laminate the cladding onto the carrier. Following that, we deposit again the optical core material layer, and we photo image the optical traces. We develop the traces, and then we seal the structure by clad 2. As we use the photolithographic process, it's obvious that we can build all the traces, all the optical waveguide core traces within one single process step. That provides a huge advantage compared to for example, the fibers, because now we can realize huge amount of hundreds or even more waveguides within one single process step. Obviously, after the waveguide processing, we'll continue the remaining electrical steps. We laminate or stack the optical layer, if we will, into the board by using irregular laminations. And here is an example of exactly that. So optical PCB fabrication flow, after forming the waveguide layer, we add the layer into the PCB, depending upon where the layer locates. But here is just an indication of N layer, N couple layer plus 1 optical in process step wise. So without emphasizing, but obviously the materials must pass through all regular processes, lamination cycles, drilling, metallization steps. So materials have been qualified to pass these steps and be compliant for the materials and tests. Finally, we route the units. we have to do, of course, the cavities, optical windows, and all that steps. We have developed process steps that utilize standard fabrication procedures so that we can really provide the OE PCB boards in a regular form factors, large panel sizes for cost and compliance for the products. Here are some physical realizations of a panel, of a PCB core panel with these transparent waveguides. So you can see here in a larger picture of a panel where we have a straight waveguides. We have a certain, let's say, overcrossing sections, indicating that really the waveguides can be built within one single layer, and we fabricate them in one single step. Another, let's say, novel attribute is that we can put them very densely, as we can cross over to waveguide channels within one layer. So these 90 degrees, 75, 45, or 50 degree overcrossings are really in one optical layer. That will increase the channel density. For example, in a fan outs, we can cross over each other, saving space and real estate on a board. Another, let's say, indication of a process, let's say, variability is that we can fundamentally add the optical layer virtually in anywhere we need it in the stack. We can utilize the full layer, or we can use it partially, as these materials are photodefinable. So here is a couple of examples of a potential stack ups with one or more optical layers. So on the left-hand side, you see single layer being buried in a middle, or then two layers being positioned on top and bottom side, quite close to the surface. In a middle section, we see that we can do them partially, just to use the space that we need for these optical traces. We don't need to utilize the whole layer. So any variation or combination is possible as the materials are processable with these flexible ways. Design tools are being obviously necessary to provide an end user potential to add the optical functionality. So EDA tool and EDA tool vendors have taken actions to have photonic layout capabilities in their software. Here are a couple of mentions: numerical cadence or light suit from Mentor Graphics. So both the simulation and the design obviously would be ideal to be accomplished within one design environment with all the needed component libraries and design rule sets. And that's obviously the work which is in progress in many of these vendors. Obviously, we can carry out the simulation using an standalone or external environment, and then feed in the design into the routing layout tool. Each, let's say, material or PCB vendor has a database for their specific material, which is supported by experimentally validated design rules for their photonic components, for their minimum bend radius, the overcrossing channels, and so forth. But adding these into the design tool gives a fairly comprehensive tool set to be used for designing the OE PCBs. Then obviously we discussed on the termination. So termination is a critical part of realizing the practical end-to-end link. We need a coupling to fibers. We need a coupling to devices. Here are a couple of examples of an industry efforts and demonstrations for waveguide compatible optical connectors from various companies and research groups now for waveguide to fiber connection. We see that the connectors vary in their let's say type. Either they are kind of edge connectors, having an in-plane connection, or they can have the 90-degree turn, which is fundamentally needed if the component sits on top of the board and you need to come up with the light towards the waveguide and turn the light by 90 degree. Obviously, the connector solutions vary in their complexity or and their alignment procedure to waveguide, but majority of the connector solution that we show here and what has been demonstrated in the industry follow the standard connector types like MT or MPO, as we see here. Some functional test results. As mentioned, the waveguide, for the waveguide practical design and simulation purposes, we need experimentally validated test results. And here are some snapshot of the measurement results of TTM's waveguides for insertion loss, crosstalk, over loss, and bend loss. So we do this routinely for every and each of the materials that we have. We look at the main characteristics with different launch conditions. And for particularly when we talk about the multimode waveguides at 850 nanometer wavelength, we can look at them obviously under different 1310 or 1550 as well, but the main application for multimode resides to the 850, so majority of the testing is done at that wavelength. These numbers will give you the design rule sets that you're needing in order to complete the physical layout and simulation performance. Another testing obviously is done at the SI side. Joshua presented the simulation extensively done. Here we show the experimental tested eye diagrams at 13 and 20 and 30 gigabits per second NRZ, and then 20 and 50 gig PAM4 correspondingly. So in this case, we looked at very long, extensively long waveguide, 94 centimeter long, which was fundamentally a spiral built on a board. No terminations in this case. It was a polymeric waveguide. So the eye diagrams indicate that we have a good performance in even with a very long waveguide in this case. Then a couple of words on the previous, let's say, the collaboration programs. Industry obviously have been looking at the waveguide technology, and here we flash out the US-driven collaborative industry effort under HDPOC. HDPOC is a US-driven collaboration, and this was one of the largest non-funded activity within the industry recently. In this program, the group demonstrated multiple waveguide technologies, two polymer technologies being a flex and an embedded waveguide in nature, as well as a glass waveguide technology. So it was a showcase of technologies, different vendors, and more so, the project demonstrated the technologies with the modular demonstrator chassis, which was later standardized under IEC TC86 Joint Working Group number 9. So test platform combined different technologies from various vendors, both on the engines, on the connectors, and the waveguide technologies. And another project I want to highlight is a significant EU effort, European consortium, which combined 20 company and academic institutes to develop technologies for next generation application. So Foxtrot, here is the Foxtrot's final rack level demonstrator platform that had really an application specific optical demonstrator designs. Here on the left hand side, we see Aurora, a multimode optical interconnect platform where we developed and showcased various connector coupling solutions, particularly. And below that is a Pegasus, which was an application, optically disaggregated object-oriented platform, test platform, more for application scenario. And moreover, the project looked at as well single mode technology and various other enabling technologies. Now, finally, obviously, the KOBO new working group Joshua is leading is a multimode waveguide interconnect system. So now this newly established group will focus on really defining the specification for the electrical and optomechanical specification. So combining the industry efforts and expertise and knowledge we have gained, we are now going to provide another, let's say, platform for specification and detailing the technologies therein. As mentioned, it will cover all the critical technical areas, embedded waveguides and PCBs, the connectors, and then the device portion. With that, I'm going to come to the summary and conclusion. So obviously, been indicated and motivated for us, power has became the first order issue and drive new solutions for development. We see that hybrid PCBs with copper and optical offers a viable 112-224 solution. We don't need retimers, no cables, and we can exploit best of both worlds. Industry and TTM do have a capability to build optical PCBs using standard high-vol scalable processes. Multimode technology and multimode waveguide technologies is mature, lower cost, and robust, thinking of comparison to single mode technology. Obviously, call for action need to start defining targeted channel specification, optomechanical specification early on for multimode interconnect system vendor compliance, and ecosystem partnering here is a key. So we need to have all players to work together to develop within the same pace and roadmap to bring multi-sourcing and technology readiness across materials connectors, EMS test developers to align these to customer roadmaps and industry readiness. With that, I thank you and hand it over to
Jim.
To you.
Yeah.
Correct. Thank you.
Thank you, Marika, and thank you, Joshua. Both very inspiring presentations. I think we can see from the level of technical detail that you've both presented that there's quite a lot going on in this space and tremendous potential for future design. So we have about 15 minutes now for Q&A. We've had a couple of questions come in from the Q&A function already, but everyone else in the audience, you are encouraged to send your questions our way. This webcast will be available as an archive, by the way, probably in the next few days, certainly by next week. The slides also will be available for people to use and to review. So with that, let's jump over to the questions. So Joshua, there's a couple right here from you for the beginning. In the 352 femtojoules per bit, when you mention that, are you also including the power penalty in the CDR that is needed after the TIA? If so, what kind of CDR that has to be used to have such low power? Because even XSR RX has higher power than that. So I think there's going to be a couple of questions coming to you, Joshua, about power consumption.
Okay. So you mentioned about the XSR. That XSR should drive this from here to this point. And the XSR and the CDR is co-located in this MPO or CPO cases. This electronics is meant to drive the fiber all the way up to the outside the world. Whereas MW's case, the optics is at most within this. So in this fiber world, they call that, this length, they call that back-to-back test. So even you're thinking of another CDR, but for the back-to-back test, you don't people don't normally consider as another CDR to test it. So as I mentioned, the electrical interface and electrical interface and optical interface is very, very short compared to general backplane connection or chip-to-chip connections, even to from faceplate to the other system. So the overall system length is very, very tiny, very small. So you don't have to have a CDR in this case. I hope this answers the question.
Okay, great. Do you have any calculations for the power savings for 224 gig SerDes for multimode fibers in the PCB?
So actually, we haven't gone to the year 224 yet, but basic fundamental calculation method is written in the white paper, which I think our team will send out after this webinar.
Okay. Joshua, while you may still have your slides there, you showed about a 30% misalignment for the TX taper. Is the link insertion loss more sensitive for RX taper misalignment after additional mode excitation during propagation?
Yeah, there must be, as I said, it is not exhaustive test yet, but you have to do a lot of combinations, not only that DMIS case, but also from the laser source to that coupler and coupler to the waveguide, and waveguide also interference with turnings and overlay of the other waveguides, and those details of stuff should be done as an exhaustive analysis. But for this, we haven't done in this paper. We haven't done a first order, viability check test. So.
Okay. All right, great. Some questions from Marika. It would be great if you could elaborate, how does the waveguide PCB handle the couple for PD and laser driver for this setup?
There are multiple ways to assemble those devices on the board. We've assembled the BGA type of devices on the board. We've used direct coupling of a device that is partly buried in the PCB itself, and we've used even a pigtail devices. So depending upon the device type or your engine or optical engine or component, we do have various techniques to apply for the waveguide to device assembly and coupling.
Okay. And there's a question asking about some more detail about the structures and material of EO-OE converters. Are they included in the PCB stack?
The converters, if we're talking about the connectors or the devices, is obviously a device which is separate from the PCB. Connector or coupler could be, let's say, and usually the intention is to have it as a permanent part in a PCB. But that's, let's say, still depending upon the case. As we saw, some engines may have an optical coupler part of it, but in many cases we may want to have the optical interface directly on the board, so we can test, we can ship the product as terminated, connectorized PCB, if you will, so that we secure the interfaces when the product leaves the gate. So Again, there are pros and cons for both approaches, but I would say that the permanent interface in PCB is the target. And now we are seeing as well couplers that are reflow compliant, because obviously that's going to be the first question as well. Anything plastic or plastic parts may not withstand these high temperatures that are required in component assembly. So that's going to be setting the first requirement set, that any optical entities or parts that we assemble on board needs to be reflow compliant.
Joshua, any comment on that?
So that it should be the separate component. It's not embedded in that stack up, because it creates a lot of cost factors in there. So for the industry to take this MUS approach, it should be your MA media adapter is separate entity, so that only solder balls or those kind of mechanical alignment should be used to assemble onto the board. But even mechanical structures will create cost factor as well.
Okay. Marika, could you comment on the availability of these PCB board designs and waveguide couplers, and the expected timeline of when this would become commercially viable?
Yeah, as we see, a lot of progress has been achieved, and a lot of development has been done around the building blocks. We know that there is not a product in the market yet implementing or using waveguides for this application that we described today. The readiness exists, so it's not going to be a huge long lead time activity, I mean, in industry in general, but we need this type of collaboration and interface, let's say, agreements and definitions and standardization that we are now doing as well in this KOBO working group, so that we do have, let's say, near standardized products or near standardized components that can be delivered. So within 1 to 3 years, we are going to see these popping up into the market.
Okay, great. So maybe we should answer some of the other questions about the KOBO working group. So there's one that asks to clarify the main intended use cases in the MWIS working group. Joshua's presentation implied that it is primarily to replace the LR SerDes for connection of ASIC to the faceplate pluggables, in which case isn't this a direct competitor to co-packaged optics, whose goal is also to replace the LR SerDes with low power SerDes? But yeah, so maybe could you comment on that, Joshua?
Yeah, I think that's correct observation, but it's the timeline is matters, because co-packaged optics is already in the on the spot right now, and many companies is looking that as solutions, but I would see this is an interim solution. So for the future-proof solution, it is a little bit of it has a little bit of issues in terms of manufacturing and system integrations, but in the end, changing it is not typically on LR solution. It could be VSR, MR, whatever solution, even XSR solutions. You could actually change it that copper trace to multimode waveguide. So it applies all high-speed track in PCB in the box or backplane. So it not only LR but also everything in PCB embedded waveguide. Also, CPO is very good technology to save the power right now at this point. So it matters there how the roadmap and timelines can support this overall changes of the innovations.
Okay, so we talked a lot about the power savings that are available. Any comment on reliability concerns of using this approach?
I could comment on the PCB wise. Obviously, new technology being, let's say, implemented into existing products needs to be tested vastly. But now we know that the material vendors who have been visibly providing their materials inherent practically from the PCB material. So the material sets are not so distinct from regular dielectrics. Could be, but let's say advanced materials. So they have been tested per se, so as a materials as well as part of this let's say hybrid stacks fairly well. Obviously, the application scenario will give a new sets of tests, and as we increase the complexity by these additional coupling elements and devices, that's another, let's say, set of testing required. So board and the optical waveguide materials are quite well tested already. The system level testing is something which the industry has to address down the road.
Okay. Just a question for clarification here as well. Somebody writes, the eye diagrams shown in Marika's slide don't show the non-linearity in Joshua's simulations. Is there a difference? And could you comment on that?
That's a good question, because that's the length and the speed is not at the same speed and at the same length, because it has a very low speed compared to the lengths that tested by Marika's test. So 10 gig and 20 gig, whereas this one is 100 gig and 200 gig distances. I mean, results.
Okay, we're almost at the top of the hour, so we just have time for a couple more questions. It looks like there's more questions than we're going to be able to answer today, but we'll get back to everyone. If we didn't get to your question yet, we will respond as soon as we can. Another big concern, and maybe this is the last one, we can get response from both of you on the cost estimates of this. Of course, it's early days, but since we're talking about PCB manufacturing costs, are they going to increase in the when you bring in optical layers?
From the PCB perspective, the materials obviously are new, but so are these new dielectrics that we have to accommodate for 100 and 224 node. So material and process wise, as we hopefully let's say highlighted, we are using the standard technology as far as we can. And currently, as the materials, these optical materials are photo definable, they comply with the existing infrastructure. We can use photo imaging tools that we use today. And processes, lamination or coating. So process and materials will not be the, let's say, the key cost adders for the PCB or PCB. Industry has to come up with the conclusion on the assembly of the parts, because the active alignment is really something which adds the cost, obviously, with the takt time or time and then the cost itself. So assembly, the devices, the couplers, there is the cost pressure for the industry.
And finally, any you highlighted design tools. Do we need more design tools or better integration between those tools and the manufacturing?
I think the design tools should design industry to focus on how that the optical design side is familiar, make that familiar to electrical design engineers. That's the key aspect. That's why I like to address the electrically equivalent as parameter extraction tools should be needed.
Okay, well, at this point we are at the top of the hour, so we'll have to end our webinar. But I want to thank both of you, Joshua and Marika. Fantastic presentations. I think everybody will have benefited from what you presented here today. We'll get back to as many people as we can in the audience who've left a question and we weren't able to answer. I'd also like to thank KOBO for presenting this webinar, and for DuPont Silicon Valley Technology Center for hosting it. So with that, thank you everyone, and see you next time.